Hi, folks. Good morning. Welcome to the 13th SRI seminar series. My name is Pranoy Suraneni. I work at the University of Miami. I'm going to talk for a couple of minutes about the Risk and Resilience Tech Hub before we hand it off to Kelly. Most of you should already know this pretty well, but the Risk and Resilience Tech Hub is a public-private partnership working across our four-county region. And its major objective is to commercialize solutions for our changing relationship to water and extreme weather. It is one of 31 federally designated tech hubs and one of the fewer that was actually funded. There are three major projects for the tech hub. One is Next Generation Concrete, which is headed by FIU. The second is Workforce and Workforce Development, which is headed by Miami TechWorks. And the third is Governance, which rests at the county. Ultimately, this is not a research project, right? We aim to make some pretty large scale impacts with respect to good jobs, thriving startups, resilient economy, resilient infrastructure, and stronger national security. Broadly speaking, there are a number of different areas that the Tech Hub addresses, including all the way from out in the water to into the land. These include energy efficiency, coastal defense, clean cement, etc. And I'm not going to go into the details of each and every one of these items. This seminar series is one of the many, many different things that we are doing. The idea of this seminar series is to kind of educate people to have a better understanding, awareness, and adoption of high TRL technologies. And for some lower TRL technologies to rapidly increase the TRL. It is critical that we establish connections between the various stakeholders and that we advance startups and technologies. The speaker that we have right now is Kelly Nix, and she's going to talk about crystalline materials and infrastructure resilience. I will not get to the details of the abstract and herself, but she's extremely qualified. She's the director of technical services at Xypex, and she's going to tell you a lot more about what she does. I only want to note the next few seminars coming up, Natrix, Dolgo, and Canopy in the next few months. And before I stop, I also want to say, please introduce yourself in the chat, type out your name, what you do, and maybe put a LinkedIn link. And if you need anything, put that out in the chat as well. So thank you very much. Kelly, it's all yours. You have to start sharing again.
Okay. There we go. Okay, so good morning, everyone. Thank you for having me. I'm excited to be here and share some details on what we're working on. It's exciting. There we go. Screens are advancing, which is helpful. We're going to go over infrastructure challenges, permeability impact on resilience, and how it affects deterioration modes, some crystalline applications and the market segments that they're applicable, proven performance, certifications, and some project references. So resilient and sustainable infrastructure, the sustainability is practice of meeting the present needs, social, economic, and environmental, without compromising the ability of future generations to meet their own. And the resilience is more the capacity to withstand or to recover from an event. Elasticity, the ability to spring back into shape. So the Risk and Resilience Tech Hub covers bio-based materials, low carbon footprint, the crack healing, withstands cracking, and extended service life with corrosion inhibitor. And Xypex can check the box on all of those. So globally, we've got a significant infrastructure funding gap. It's projected to exceed $15 trillion by 2040. And a large portion of this is actually transportation. 8 trillion alone is representing roads. At the same time, the infrastructure is being exposed to increasingly aggressive environmental conditions. We're seeing higher frequencies of intensity of freeze-thaw cycles in colder regions, extreme heat in hotter climates, and widespread exposure from chlorides, both marine and de-icing salts. In South Florida there, the de-icing salts aren't really the driver, but you certainly have your marine environments, and everything corrodes. So these combined pressures are changing how infrastructure is evaluated. With limited funding and higher risk of deterioration, owners and engineers are placing greater emphasis on durability and service life rather than just the initial construction cost, which is something that we as an industry have been pushing for quite some time. So when we look at mature markets, the reality is very clear. Infrastructure is no longer primarily about new construction. It's about maintenance, repair, and replacement. In the US alone, there's over 600,000 bridges, with more than 40,000 already classified as being in poor condition. And there's also approximately 200,000 bridges that require major repair or replacement. It's the same in Europe, where between 50 and 70% of transportation budgets are allocated to maintenance and replacement rather than new infrastructure. And countries like Germany, Italy, France, they're investing heavily in rehabilitation programs driven by aging infrastructure and high-profile bridge failures. So the key takeaway is that in mature markets, the challenge is not just building new assets, it's also managing and extending the life of the existing ones. So the shift is critical because it places durability and long-term performance at the center of the decision making. In countries like China, the scale of infrastructure has been massive, but now we're seeing a transition towards maintenance and long-term performance. Japan has an approach where they've got stock management, so they even relatively new structures are moving into their urgent maintenance categories. Large-scale projects in the Middle East are being designed with service life expectations of 100 years right from the outset. Latin America, there's still a significant need for new infrastructure, with investment requirements estimated at around 3% of GDP. I'm sure you can understand the issue with that. That is not an easy budget to control there. So the frameworks are based on total expenditure or life cycle cost instead of just the upfront construction cost. So the direction leads to a more durable, longer lasting decision-making process. So infrastructure is a durability-driven segment. The infrastructure networks are aging faster than they're being replaced, and it's creating a growing backlog of structures that require maintenance, repair, and rehab. And second, in mature markets, maintenance now consumes the majority of the transportation budgets, and this fundamentally changes how projects are prioritized. At the same time, environmental exposure is becoming more aggressive, accelerating deterioration processes across all regions. And in emerging markets, we're also seeing the introduction of long service life requirements. Funding constraints are increasingly scrutinizing life cycle performance, pushing decision makers to focus not just on initial costs, but on long-term durability. So we'll get into how concrete permeability impacts infrastructure. So is concrete waterproof? In general, no. Concrete's microstructure is porous. As the cement paste hardens, the excess water leaves behind the interconnected voids and capillaries. In a typical 0.40, 0.45 water cement ratio mix, only 0.27 of it is actually the water required for hydration. The rest is water of convenience. And as that water leaves the system, it leaves behind interconnected networks of pores and capillaries, which are a highway for water to come through. We're all aware that cracking in concrete construction is pretty much inevitable. Concrete's ability to self-heal is limited to cracks that are approximately 0.15 millimeter, while drying shrinkage cracks can often range from 0.1 all the way up to 1.0 millimeters. And those cracks provide a direct route for water ingress and everything it brings with it, your chlorides, your sulfates, and your other corroding materials. The most sustainable concrete structures are those that don't require rebuilding. Concrete's durability is directly related to its permeability. Pretty much all modes of concrete deterioration are all reduced by lower permeability. So sulfates, chlorides, microbial-induced corrosion all require some fluid transport into the concrete pores and capillaries. Less deterioration leads to longer service life and better resiliency. So the core failures, transport enablers, water permeability, capillary absorption, and crack formation is transport pathways. Chemical attack, your chloride-induced corrosion, again, being based out of South Florida, you're all very familiar with that. Carbonation and the pH reduction that is the catalyst pretty much for the chloride-induced corrosion. Sulfate attack, alkali aggregate reactivity, which is localized in certain areas, not everywhere, but can be a big issue. Your physical and environmental stresses, so freeze-thaw cycling, thermal cracking, abrasion and surface scaling, as well as your initial construction defects, so tie holes, joints, inadequate cover, or poor consolidation are all issues that can affect the service life. So these interconnected capillary pores allow water for the transport for aggressive agents. Reinforcing steel needs water and oxygen to oxidize. When ion diffusion occurs over time, the cracks dramatically accelerate the transportation, and the time to corrosion initiation depends on permeability. If you can limit water ingress into the concrete matrix, reduce permeability of the cementitious system, prevent aggressive ions from reaching reinforcement, and if you can control cracking and transport pathways, you can achieve durability, long-term resistance to chemical ingress, and protection within the concrete matrix. So the benefits of crystalline for concrete durability, you've got crack healing, which is unique to crystalline, reduce chloride ingress, increase sulfate resistance, acid resistance, carbonation. You get an extended service life and an improved asset reliability. A little bit of background on crystalline. The first patent was actually issued in 1946. Now it's not the version that's available today. That was patent-based, and it was a mono reaction only with calcium hydroxide. Once the patent expired, though, the technology was further refined to react with soluble salt complexes and the byproducts of cement hydration, as well as the unreacted cement. Created a more robust and stable crystalline complex, so it's able to withstand chemical attack. And also, it's not competing for the calcium hydroxide with SEMs. So with the newer versions, or newer being 1969, you can use higher SEM replacements because you're not just competing for the calcium hydroxide, it's reacting with the other salt complexes. Then we got into the 1990s and into the 2000s, and a variety of other products were brought onto the market utilizing the crystalline chemistry, repair products, admixtures, different set properties, pigments and tracers, and with that, there's over 30 years of performance of the admixtures in field performance. So how it works in general, the byproducts of cement hydration and unhydrated cement are the particles lining the capillary tract you see here, also within cracks. The pink dots indicate the Xypex coating diffusing into the capillary. When the crystalline chemistry comes into contact with the calcium hydroxide and the other byproducts in the presence of water, non-soluble crystalline is formed and is permanently fixed. It's within the pore structure. And what it does is it fills in the capillary or the crack in such a way that it creates a tortuous path. So there is still airspace there. It does still breathe. There's no expansive or tension forces applied to the concrete. But as you can see, it can withstand even high hydrostatic pressure. The crystalline chemistry is also a catalyst. So it's not consumed in the reaction. It is still available to react later down the road. So it behaves as a scavenger within the pore structure. It collects calcium and pore solution ions, transports them, then deposits the calcium in the pore solution ions, and it frees up to bond with more ions. This results in a modified microstructure that blocks the ingress. On the left, you can see an SEM image with no crystalline present. And on the right, obviously, you can see it with crystalline. And that creates a tortuous path so that the water can't get through, even under fairly high hydrostatic pressure. There's testing up to 400 feet of head pressure, and it withstands. Another product with the crystalline that we have for infrastructure that has to do with wastewater is a antimicrobial combined with crystalline chemistry. And what it does is when you've got a situation where you've got microbial induced corrosion or the potential for microbial induced corrosion, you see this in wastewater systems where you've got long, slow collection. You've got anaerobic conditions in the effluent. What happens is that generates H2S in the effluent. Then when it comes into an area of turbulence, either flowing into a manhole or you've got a lift station or something of that nature, the gas comes out of solution, much like shaking up a can of pop and opening it up. The gas comes out of solution really easily. And there's bacteria in the airspace, in the system, that feeds on H2S. So it consumes the H2S, combines it with water, and excretes sulfuric acid as well as sulfates. So these bacteria live on this in the biofilm, in the airspace, generating this acid. The acid then flows down the structure, and the concrete is subject to both acid attack as well as sulfate attack. So with the antimicrobial, it kills on contact, so it disrupts the cell wall, but it's also combined with the crystalline chemistry so that any cracks that appear in the concrete substrate or any sort of damage that occurs, it's able to self-heal cracks up to 0.5 mil. It's also available as a repair mortar. So when you've got a situation such as this one where you've got aggressive microbial induced corrosion, this is some product that it's a structural repair mortar that can be used to reinstate concrete cover and save a structure that would otherwise need to be removed and placed. So the admixture is ideal for precast, cast in place, concrete, and shotcrete. So it's a fixed mineral solid, kills bacteria on contact. There's no need for liners or coatings. In fact, you don't want to cover it with any sort of a coating because it kills on contact. Saves your time in production and installation and extends the service life of the concrete and the wastewater structures. It protects not only from the acid attack, the sulfate attack, but you also have the crack healing in there and the waterproofing. So applications where you'll find crystalline used in many parts of the world. We've got bridges, tunnels, marine, water, wastewater, below grade foundations. Many projects have been utilized over the last 50 some odd years. New structures as well as existing structures and repair and rehabilitation. So when we're talking about that infrastructure gap, the repair materials come into play too. And those products are available as admixtures, coatings, and mortars. For the admixtures, they're added to the concrete at the time of batching. So they provide integral waterproofing, making the concrete more durable. You have less labor on site. You don't have to worry about weather. So if you're waiting to put a membrane on something for the concrete to cure out or for good weather to do something that requires adherence, that's all saved in using an admixture. It's compatible with a wide range of concrete mix designs, admixture suites, raw materials. It's suitable for above and below grade. It doesn't interfere with air entraining. We have different formulations that are available for different set properties. Some are set neutral, some have a slight set delay. And we also have a visual detection system for quality verification. So in lower trust economies, sometimes there are counterfeits and whatnot. We have the ability to ensure that it is Xypex in the product. We also have an admix available, as I mentioned, with the antimicrobial. So this is Biosand C500. This is for wastewater applications. or anywhere where you've got the presence of H2S and you're concerned about microbial-induced corrosion. It's the only admixture that combines the antimicrobial and the crystalline, and it is also available in a repair mortar. So surface applied coatings, if you've got a structure that's existing, it's leaking or it's showing some signs of deterioration, or even if it's new construction, but the way that it is constructed, if you've got very large, thick, massive concrete structures, you may go with a coating instead of the admixture. It's applied as a cementitious slurry to the surface. The chemicals penetrate through capillary action, so all of the products are applied to a saturated surface dry substrate. So again, you don't have to dry anything out. You don't have to wait for, if you were going to do an epoxy liner, you'd have to wait and get the concrete dry ahead of time. You don't have to worry about that. All the products are applied, saturated surface dry. So that saves a considerable amount of time on site. Reacts with the moisture and the cement byproducts to form the insoluble crystals, and the crystalline growth blocks the pores and micro cracks. It's also suitable either negative or positive side. So one issue with existing structures quite often is that you don't have access to the positive side. So repairs are quite difficult if you have a leak. These products are suitable to be applied on either the positive or negative side, and it won't be pushed off by hydrostatic pressure because it diffuses into the concrete. Repair and rehabilitation. So if you've got an active leak, we have a patching material. It's a rapid set. It will set up in about 3 minutes, so don't mix a whole bucket of it or you will have to get another one. It's used to seal cracks, tie holes, and defects. Cement-based and compatible with concrete and masonry. It is certified for contact with potable water as well, so it's not harmful. And it's good for joints, pipe penetration, honeycombs, etc. Our repair mortars, we do have a Megamix 1, which is a acrylic modified thin parge coat. That is our method for rapid return to service. So if you need to take a structure down, repair it, and put it back into service quickly, the Megamix 1 is recommended for that. Also certified for contact with potable water. Our Megamix 2 is a high-strength repair mortar, and that is the one that can also contain the biosand if you're in a wastewater sort of application. It's got excellent adhesion, low shrinkage fiber reinforcement. It's high strength, reduced chloride penetration, and it's suitable for structural repair. It can be applied in lifts up to 50 mil, and you can do multiple lifts. So if you need to reinstate deeper repairs. So when it comes to proven performance, Xypex has been around for 55 years. So we have quite a few test results. We, in fact, have a method of sort of cataloging and a library of different test results. We're the most specified crystalline material in the world. And so when someone's doing a study or doing a thesis, whatnot, typically Xypex is included in those studies. And we have quite a bit that we've done on our own. Some examples are the Electricity Generating Authority of Thailand wanted to do some repairs to their cooling towers. So they were using seawater in their cooling towers. And as a result, the concrete in those structures had undergone some pretty severe chloride attack. So they used concentrate and modify to treat the damaged concrete and extend its service life. And in order to ensure that the Xypex was working, they cored at an age of 21 days, 30 mil cores, and sent it in for SEM. As you can see on the left, the untreated concrete pour there has no crystal development versus the one on the right, which is actually not even at this, it's at a lesser magnification. You can see the crystal growth in the pore space at an age of 21 days. And typically, as with most reactions with cement, 28 days is typically when you would evaluate it. Japan has a habit of using our concentrate on bridges. They believe strongly that it improves the durability and makes the concrete better. So they did this study here where cores were extracted after 10 months of service. Untreated cores had continuous leakage in their apparatus, a water flow of up to 5 millimeters per second. And the treated cores had an initial minor leak that gradually stopped. And the microscopic analysis confirmed that it was the crystalline that sealed the cracks. So even in existing bridge structures that are already seeing cracking, this is a strategy. This was a water reservoir in Qatar. There was 2 potable water tanks. Over 56,000 square meters were treated with surface applied. As with most tanks, when you initially fill them, there's a greater pressure put on the structure and they tend to belly out a little bit and crack initially. So you can see here on the left that this structure was filled on May 24th. There was some initial cracking and leaking, but by June 2nd, that same structure was dry and there was no repairs done. This was just with the active crystalline. Oklahoma DOT did quite an extensive study on cost of ownership and different strategies to get to 100-year service life for their bridges and their infrastructure assets. So they studied Xypex compared to conventional galvanized reinforcement. And as you can see here, the corrosion rate was significantly reduced with the Xypex plus the same rebar. And the authors theorized that it was the crack healing that resulted in the reduced corrosion. This is from the table showing that the cost of ownership. So initially there is a little bit of a higher cost, but as you can see, the time to repair in years is almost 50% greater for Xypex. So it extends the time to first repair, and the total cost of ownership is reduced by about a third. And that's an 8-inch deck, 60 mil cover, 100-year design. Again, time to first repair is increased by 50%. The amount of corrosion in uncracked concrete was reduced by about 40%, but in cracked concrete, the amount of corrosion was reduced by 70%. And I think you'd be hard pressed to find a piece of infrastructure that doesn't have any cracked concrete. So the results of this were quite interesting. When it comes to acid exposure or corrosion, chloride corrosion, Japan did quite a bit of research on this. So they subjected the samples to a 5% sulfuric acid solution or about a 0.9 pH for 100 days. Now, Xypex advertises that our products are rated for exposures of pHs from 3 to 11 in constant contact, 2 to 12 in periodic. So this is well outside our published range. But even at that, at a 0.9 pH, the untreated concrete mass loss was 21% versus the Xypex treated was almost half. So 11.7%. Then with the corrosion study, the results demonstrate that reducing the permeability significantly limit the chemical ingress and the deterioration mechanisms. The corrosion area was reduced by approximately 50%, and the chloride content was reduced, again, almost half. With the NT Build 492 rapid chloride mitigation, this was done in China. So to evaluate the chloride transport for a sea crossing, the test measured how quickly chloride ions could move through the concrete. A voltage was applied across a concrete specimen to accelerate the migration, and the penetration depth was measured using silver nitrate indicator. And that's how you get the chloride diffusion coefficient. 3 different concrete mix designs were evaluated, and the initial chloride diffusion coefficients ranged from 5.23 to 7.22, and after treatment, it was reduced to approximately 1.49 to 3.26. So reduced the chloride migration by roughly 27%. Carbonation resistance. So this is a 4% CO2 concentration 40 degrees C, or approximately 110 Fahrenheit. And the Xypex treatment reduced carbonation depth by 35 to 40%, and the coefficient was also reduced by a similar amount. And those depths were measured at 28 days all the way out to 91 days, and the results consistently showed the reduction in carbonation, which, as we all know, reduces the pH of the concrete, eliminates the passivity layer on the rebar, and then allows corrosion to begin. So the Xypex crystalline structure is not only reducing water ingress, but also chlorides and carbon. So all of the factors that combine to corrode rebar, Xypex provides protection from. Extended service life studies, we have a number of these as well. These are studies that I speak about quite frequently. This one is built in 95, near marine conditions, so it's in sort of an estuary. 0.45 water cement ratio, 51 mil concrete cover, and the condition assessment after 26 years in service, cores were taken and chloride testing was done. Based on the depth of carbonation at that point was 2 millimeters after 26 years in service in a marine environment. And based on fixed law, the predicted age of when corrosion would initiate on this particular structure is 187 years after 26 years in service. A similar structure, these studies were done in Australia. This one was not too far from the first one. It was built in 94. This is in a splash zone with chlorides, less concrete cover on this one. So this one only had 40 to 45 mil concrete cover. And after 19 years in service, the condition assessment was done in 2013, and the service life is predicted at 129 years, again, with less concrete cover than is typical. Another long-term study that we have done, this one is probably one of my favorite ones to talk about. It's a 10-year study, over 225 sets of concrete, 160 projects, 5 countries, all different cements, SCMs, SEM replacement levels, raw materials, so your sand and gravels, as well as your admixture suites. When concrete was delivered to site, treated with Xypex admix, samples were requested back, and these particular projects were able to provide those samples of concrete delivered to site that was placed. So real concrete, not lab concrete. And they were tested at various ages over time. And the findings of that were the average permeability depth at an age of 28 days, so just when the reaction's getting going, is 15 millimeters, or just over a half inch. But over time, when those same concrete samples were tested at a year, the permeability was down to 2 millimeters. So the crystalline technology continues to work over time. It is not consumed in the reaction. It is available to react for the life of the structure, and should cracks open up at a later date, they will continue to crack heal. The percentage of samples that had zero permeability at 28 days was 3%. Again, that's not unexpected. 28 days, the crystalline's just getting going. When it gets out to a year of age, 57% of the samples showed zero permeability. So it is a long-term improvement over time. And that was when it was exposed to 0.5 MPa. It's all under the EN 12390 test method. ASTM is in progress of developing a permeability test, but it will likely be based off of EN 12390. Again, with the sulfate attack, sulfates are present in groundwater, seawater, wastewater, a variety of different sources. This testing was done on a basic 30 MPa, shows a 97.9% reduction in mass loss when exposed to sulfate. The concentration is 36,000 milligrams per liter, and it was done over the course of 4 months. So you can see the untreated concrete on the left is showing quite a bit of deterioration, and the treated sample is virtually intact. With the biosand admixture, the antimicrobial, it kills the acid-generating microbes present in sewerage environments. Testing in accordance with ISO is showing a 99.98 reduction in bacteria. I believe it needs to be 99.99 in order to have any sort of health claims. So we are just under the wire there. We do not qualify. We do not make any health claims because of that, but we're very close. So this test was done. This one here is the samples were hung in a live sewer for 10 years in total, but these particular photos were taken at the 6.5 year mark. So the one on the left, you can see the degradation here versus the one on the right is treated. So this wastewater treatment plant here that we're hanging in, it was a covered sedimentation tank. The H2S range was between 20 and 70 with an average of about 40.7 parts per million. The average humidity was 79%, and they were hung over 10 years. We also have the corrosion rate relative to control. So the untreated is as the control, and the Xypex treated had a 9 times reduction in corrosion rate. And when, based on the corrosion that the samples experienced, the service life for the untreated was estimated to be about 25 years, whereas the service life for the biosand treated was approximately 125 years. So the service life was increased by a factor of 5. We've also done quite a bit of work on sustainability. We have EPDs and HPDs for many of our products. We also commissioned a study for carbon footprint accounting. And based on 1,000 square meter foundation, the CO2 was compared to more traditional waterproofing methods. So your hot applied rubberized asphalt and your HDPE membrane sheeting. And both our coating and our admixture were compared, and there's approximately a 60% reduction in carbon dioxide than traditional waterproofing. So we also check the box when it comes to using sustainable materials, green purchasing, and any sort of, you don't typically get into green building programs when you're building a wastewater treatment plant. However, it is good to know that we are also checking the boxes on that side. So certifications, again, we've been around for a very long time. We are active around the globe, so we have many, many certifications. We're the only ones approved as a waterproofing admixture. Most other admixtures are classified as water resistant, and that's based on absorption testing versus water permeability under pressure. So I referred to before the EN 12390 test method. This particular assessment document is in accordance with water permeability testing, not passive absorption. Obviously, we hold C494. We're also under EN 934 drinking water standards in Australia, etc. We're certified for contact with potable water. We can be used in enclosures at zoos and have been used in a number of those. Obviously, water treatment, wastewater treatment. International codes were certified as waterproofing and damp proofing under ICC. We have British Board of Agreement, Dubai Certified Laboratory. If you can name a certification, we are probably in progress, or we already have it from the to-do list here. So again, sustainability, we reduce carbon footprint. We've got the documentation to support you in your green building projects, and we have the test data for improved durability of structures. Our products are a permanent one-time application. They lower your maintenance costs and extend your time to first repair and extend the service life overall. Now, this technology is available around the globe today. I know that the Risk and Resilience Academy here is looking for solutions that can be used today, that can be scaled and implemented. We have manufacturing in 13 different countries. We're distributed in over 100 countries. We're compatible with other materials and admixtures. And again, being in business for as long as we've been and test results from around the world, we have the backup for that. We also have a full complement of accessories and repair materials for a full system. The stars here on this map indicate our manufacturing locations. So Richmond, British Columbia is where I'm speaking to you from, the upper left-hand corner there in Canada. But we have a plant in Parkham, Germany as well, and Albury, Australia. We have licensees in India, China, Brazil. All the red dots are different distributors that carry our products. So regardless of where your project is located, we can get products, including in Mongolia. So different project references. This one here, Admix C1000 was used in a site redevelopment here that became the Google campus in Germany. As you can see, the lower left here, there's some water ingress, and the upper right, you can see where the water was coming in. Conventional membranes and injections that already failed on this site, and crystalline waterproofing was selected. There's hydrostatic pressures of up to 15 meters. This project here, I would love to go visit personally. It's a floating pool in Istanbul. So you've got saltwater marine environment on the outside, and you've got chlorinated water on the inside. And Admix C1000 is the only waterproofing on this particular structure. In heavy industrial, this one here is the largest single pulp facility, was $22.2 billion and a 4.5 million square meter footprint. Aggressive chemicals, industrial chemicals, water, high temperatures, you name it, this job is subject to it. And admixture was selected due to the service life requirements for this particular project in Brazil. The Sanofi Pasteur, this one here is a vaccine manufacturing plant, came on board in the middle of COVID. As you can imagine, there was quite a bit of expansion into those sorts of projects at that point in time. And for this one, the contractor actually selected using Biosan C500 and C500 in this project because they were responsible for the first 10 years after completion. They're responsible for the maintenance of this particular structure. And the contractor had seen our products and believed in our products and felt that it would reduce their risk on the maintenance cycle to use Xypex. So below the water line, they used Admix C500 for the waterproofing, crack healing, and acid resistance. And then in the approximately a meter below the water line and up into the headspace, they use the Biosan C500 for protection against microbial-induced corrosion. Lambeau Field for football fans out there. It was originally built in 1957. It was much smaller. It's gone through many renovations. And in 2017, they increased the capacity to 81,000 fans, which as they scale up the capacity, obviously they've got to scale up the wastewater system. But again, the nature of the stadium, you've got heavy use over the course of, call it 5 hours, 8 times a year, and the rest of the time the structure is sitting fairly empty. So they chose to expand the wastewater system by putting in surge tanks. So those tanks capture and hold surge volumes and then meter it into the wastewater plant at a slower rate. Because of that, because of the long retention times, though, it is prone to microbial-induced corrosion. And so Biosan was chosen for its protection. We've got a cement plant in Greece, so even cement plants are, are choosing Xypex. These silos are at a marine facility at a loadout. They had deteriorated due to chlorides, much like you would see in your environment there in southern Florida, and they required restoration. Obviously, if you've got holes in a cement silo, that's not going to go over well. So the surface was coated with approximately 2,500 kgs of concentrate and to extend its service life. We do a fair bit in tunneling as well. So the Cairo Metro line in Egypt, the initial waterproofing system had failed and a negative repair strategy was needed. So again, there's very few options when it comes to negative side repair, but we are able to help you out there. So concentrate was selected to repair the areas and provide waterproofing for stations and water tanks that had been leaking. And I've got a local one here for you. We've got clarifier tanks from Hollywood, or the city of Hollywood, Florida. They chose to repair and rehabilitate two clarifier tanks instead of replacing them. And this was selected due to carbon footprint. They were looking at the carbon footprint of a new build. So our Megamix 2 was spray applied to 55,000 square feet and reinstated the rebar cover and the functionality, extending the service life. So basically, crystalline waterproofing works. It's been around for over 5 decades. It protects structures from deterioration in aggressive environments. It can be used to rehabilitate existing structures and enhance performance, extending the service life. You've got crack healing capabilities, improving the reliance of the infrastructure, increases durability, service life, and it's available around the world today. Thank you.